Alright, it's Nobel Prize week 2023, which means it's the 1 week out of the year when we care what Sweden thinks. So today is Tuesday, which means they announced the physics prize. The recipients are these three scientists, and they got it for basically developing the technology to create videos like this. What you're watching here is a slow motion of an electron riding on top of a wave of infrared light. And if that doesn't blow your mind, here's why it should. Think about trying to take a video of a hummingbird. These guys flap their wings at 50 beats per second. Which means in a normal camera, those beats are going to get blurred out like that. See? What you really need is a high-speed camera at 1500 frames per second, and then you get to see the intricacies of how it's, doing its thing. The point is that if you want to study an object that is changing really fast, then you need your measurement device to be even faster. And sure, hummingbirds are fast, but it's nothing compared to the speed at which things happen at a microscopic scale, like I'm talking atoms and molecules. Like this reaction of oxygen and hydrogen combining to make water. This stuff happens at the femtosecond scale. A femtosecond is a millionth of a billionth of a second, and it's how long it takes light to go from one end of a virus to the other, like the COVID-19 virus. And the craziest part about this year's Nobel Prize winners is it's not even about femtoseconds, it's about attoseconds. An attosecond is 1,000th of a femtosecond, and it's how long it takes light to go from one end of a hydrogen molecule to another. Okay, here's another mind bender. There are as many attoseconds in a single second as there have been seconds, period. Like since the beginning of time, since the Big Bang. And you might be thinking, what can we even study if we make measurements that fast, right? And the answer is electrons. Here's a weird cartoon that the Nobel Committee came up with of electrons doing something shady, I guess, and getting caught in a spotlight. I don't want to speculate on what the electrons were doing, but the idea is that the spotlight has to be at the attosecond level in order to catch electrons doing their thing. And for the longest time, people actually thought this was impossible. You can improve laser technology, but only up to a certain amount. And they had done that and gotten it to around 30 femtoseconds. But getting to that attosecond level required new physics. And that's where our Nobel Prize winners come in. So we're going to start with Anne Lavoisier. I don't know if I got that right, but it's French, so it's hopeless. So back in the 80s, she was doing experiments with lasers going through gases. And she noticed that if you turn down the frequency of the laser, so down to infrared, the gas would start producing harmonics on top of that laser. So for the musicians out there, you already know what this is. These are the overtones that you hear when you play an instrument. And with musical overtones, the higher the overtone, the less loud it is, right? And see, that's not what was happening with the laser's overtones. So here you can see that as you go to higher frequency, what you would expect is a gradual decay. But there's a little plateau where for certain frequencies, the intensity remains the same. And that's a hint at some new physics. There's something weird going on in there. So the team came up with this 4-step explanation, and it involves a single electron interacting with that laser light. Okay, so step 1, the electron's inside the atom, really close to the nucleus. And then that laser light comes in, the red laser light, and the electron gets kicked out. Now here's the crucial part. So it's gotten kicked out and it wants to leave. But remember, light is a wave, which means if it pushed one way, it's going to push back the other way as the cycle continues. As it gets dragged back, it's going to dump all of that energy into all of these other overtones, And that's why you have those overtones that get reinforced and they don't actually decay. Okay, so now you got some overtones. Now what? And that's when the next two Nobel Prize winners come in. Pierre Agostini and Ferenc Krausz. These are the guys that took that idea and used it to make attosecond light pulses. And these guys used the oldest trick in the physics book, interference. So the idea is the following. On the top there, you've got two gray waves of slightly different frequencies. When they line up, you get this little wave packet where they constructively interfere. And when they don't line up, you get destructive interference and they cancel each other out. And that's the whole idea. They took those overtones that came out of that gas, and then when those overtones would line up, you would get this attosecond pulse. And then when they wouldn't line up, you'd get destructive interference and you wouldn't get a pulse. And here's a schematic of what a typical experiment like this looks like. So you got lasers coming in, it gets split up, and over here it goes through a gas, and then it makes that pulse train, and then it moves through and goes into the sample, and that's where you image those electrons. And here's actually Krausz's lab in Max Planck, Germany. You know, a bunch of electronics, a bunch of laser light, all to image these tiny, tiny little movements of these electrons around atoms and molecules. And now if you're one of those people who's wondering, you know, what's even the point? What's the practical use? First of all, find some joy in your life. But second of all, you can use this kind of technology to come up with new medical diagnoses, new materials for the future. I mean, we need all of that stuff. Personally, for me, getting a video of an electron surfing on a wave of infrared light is good enough for me. I mean, just look at it. I mean, you know how people say, like, you know, quantum mechanics, wave particle duality. Here you can literally see the electron wave like interfering and moving up and down. I mean, come on, that's